Let's go. Recall. What did we talk about last time? What is fun lim at? You give me a function, f on the reals. You give me a limit, it's a real number at L, and you give me where it's supposed to be, where it's supposed to have a limit at. It's a prop. What is the prop? All together now. For all epsilon, exists a delta, so that for all x not equal to c, this is the difference between limit and continuity. X not equal to c, if x minus c is less than delta, then f of x minus f of c is going to be less than epsilon. Okay, everybody remember that? And then we're proving. Thank you. Minus L is less than, I don't know what that was, epsilon. As opposed to, let's just recall, function is continuous at you give me the function and you give me the point, and the definition is for all epsilon, there exists a delta, so that for all x, no, not restricting away from c, x minus c is less than delta, implies f of x, now it is f of c, is less than epsilon. Okay, not f of c here, yes, f of c here, not equal to c there, any x here. Great. And we were looking at, I think last time we proved, which direction we proved last time? We proved forward. We proved that if, now I don't remember which one's the forward. Forward depends on which order you had the things. Okay, we're going to prove the limits. We proved if f goes to L as x goes to c, then for all sequences xn converging to c, never equaling to c, f of xn, that's a sequence of numbers now, converges to L. Okay, that's what we did last time. Conversely, today is the converse. Conversely, if for all sequences xn going to c but never equaling c themselves, the sequence fxn goes to L, then f goes to L. Then the continuous version also holds. Okay? How are we going to do this? Joe, you got an idea?
The fact that all sequences go to C, that means that there's always any, like, what's the mathematical term for, like, any ball, that's the term I'm thinking.
Yeah.
Any ball around our point C, there's always a sequence that contains any point in that ball.
Okay.
That we can get arbitrarily close to this is just the foundation of the idea, but
yeah, let's draw a picture. Let's try to argue with a picture. Okay, so here's our function f. Here's our point c. Okay, here's the value, although it doesn't matter what the value is, actually. Maybe I should draw it like this just to prove the point that this has nothing to do with continuity. It's just about limits. So anytime you have a sequence of real numbers that converge to c without ever equaling c, so maybe this is x1, and this is x2, and x3, and x4, and x5, and x6, and so on, and they're getting closer and closer to c, then the values, the set of values you get, so this is f, so over here is f of x1, and over there is f of x2, and so on. So these f values converge to L. That's what we know. Why is that? Just the fact that we have these dots, these sequences of dots, but any sequence of dots somehow is supposed to tell us that there's going to be an entire window around C that's going to make the image an entire window around L, no matter how small a window around L you take. In fact, if I didn't tell you already that this was a theorem, maybe you would think this is false. Like maybe I can take all the rational sequences, but on the real, the sequences are count. We haven't talked about countable and uncountable. Maybe some of you have heard of that. We need to talk about countable versus uncountable, and maybe we will in a couple of weeks. But sequences are a countable thing, whereas limits are a continuous thing, are uncountable. Maybe sequential limits aren't strong enough to capture continuous limits. Are they or aren't they? That's the question. Well, they are because I'm stating it as a theorem, right? I should have like a is it true or is it not true and a left and a right. You have to decide which is the case. Yeah, let's use the extra space for now, and then we'll come back to the theorems. So why? What is a good thing to do when you're trying to understand a problem? You think something might happen, but what if it doesn't happen? What could go wrong, right? What could go wrong is a very good question to ask. So what could go wrong? What could go wrong? What would it mean if, I guess I'm just supposing we do this by contradiction, right? But what would it mean if this was false? So if not, then it's not true that for all epsilon there exists a delta. So if not, then yeah, there exists some epsilon, so that for all delta, no matter how small, there exists an x not equal to c. X minus c is less than delta. Right. And the word but mathematically means and. Okay, so it's no longer an implication. It's an implication when it's a hypothesis. When you negate it, it has to become an and. So what does that mean? There is some epsilon. It's not true that no matter how small an epsilon you take, there's going to be some delta here so that these two things happen. That means there's some epsilon where no matter how small you take delta, there's some window epsilon. Let's make this the bad window. Here's the bad window, epsilon, from there to there, okay? This is L plus epsilon, and this is L minus epsilon. No matter how small a window you take here, there is no small enough window. So there's some uniform window on the side in the y-axis on F, so that no matter how small you make this window here, there's always some point where the value of this point is within delta of c, but the function value is outside the window. What can we do with that? Something.
But that can't happen because of the fact that the limit exists. Like we have a limit though, so.
Well, we're trying to prove that we have a limit.
But we have the sequence of stuff.
What sequence?
The sequence of f of r and
What xn's? Give me, where are we supposed to get an xn that goes to c?
Intro sequence. And then you can specialize. Yeah. Epsilon. Well, you can choose an epsilon. Yeah, you can.
Okay, so let's choose the epsilon. I'm with you. We know that there exists an epsilon, right? So this was like, what could go wrong, aka by contra, and let's call that hypothesis H. And then we push neg at H. And then you're telling me choose epsilon and epsilon positive, and then H epsilon using H. And now I have the epsilon, and I know that for all delta, there exists an X. So what?
For delta, like, I could be wrong, but my hypothesis is you specialize our sequence limit to epsilon, then you take the n, and then you use the f of n, or f of xn n.
What's xn? I need to get an xn. I need to construct the sequence.
Can you do that in box choose and get a subsequence like for all deltas? If you plug it in, you get an x that's not equal to c, and the rest of the statement.
Very good. Let's think about what H epsilon says. H epsilon is this part. It says for any delta, you can give me a proof that delta is positive, I'll give you an x. That x will be not equal to c, and that x will be within delta of c, and f of x minus L will be at least epsilon.
Yeah, so there'll be like a function that.
Exactly. This is fancy choose. Okay, this is the fancy choose. So let's choose, what do you want to call this function? I guess we could call it delta of epsilon. You want to call it delta? That's okay. So we'll choose the function delta. Delta will be, yeah, okay, fine. Let's call it delta. Let's call it delta. So we choose delta. That's going to be a function from epsilon. Sorry, we already have epsilon. From delta to x. So maybe delta is the wrong name for this function. We should call this function x. Choose x. And then the fact that x is not equal to will be called xne. And then the fact that x is within this will be called x to c or something, xc. And then this maybe we'll call fxl or something using h epsilon. What will that do? That will give us x, which is a function from what to what? Exactly. It takes a delta. It takes a proof that delta is positive, and it returns exactly a real number. It returns a real number. And then what is xne? It takes a delta. It takes a proof that delta's, let's call this H delta, or delta pos maybe is a better name for that. Delta pos, a proof that delta is positive, and it returns a proof that x of delta and delta pos, which is now a real number, is not equal to c. Everybody see that? And then we're going to get an xc. Xc is the same stuff, but that returns that x of delta and delta pos minus c is less than delta. And it returns an fxl, which says that given delta and given that delta is positive, it returns f of x of all this stuff minus L is at least epsilon. Cool. Fancy choose. Gives us functions. I still don't have a sequence. Where am I going to get my sequence? How?
Need a sequence of deltas.
Yes. We're saying continuously delta goes to 0, but we don't have to do that continuously. We can make delta equal to 1 over n. 1 over n is an excellent choice. Okay, so the sequence that we want, what should we call this sequence? U or something? U is going to be a map from n to r. What is it? It's a function that takes n and maps it to x of delta equal to maybe 1 over n plus 1, just to be 1 over n plus 1, together with the proof that it's greater than or equal 0, which is by bound. By bound. I think so. 1 over n plus 1 bound should prove that 1 over n plus 1 is positive. Okay? So does everyone understand what these u's are? We set delta equal to 1 over n plus 1, really delta sub n. And the negation of the thing that we're trying to prove says there's some value x, there's some bad value x. Call that u. What we just constructed is a sequence. It's a sequence that's going to have the property that the sequence is going to C, and it's going to have the property that the sequence is never equal to C, and it's going to have the property that, that's going to be a contradiction from the hypothesis that any sequence that's not equal to C that converges to C F along that sequence also converges to L. That's where we get our sequence. So we need fancy choose, and then we need to get the sequence. Does that make sense, John?
How does this translate to like natural language?
Yeah, in natural language. So let's do it in natural language. Okay, let's finish the proof in natural language. Let's prove the whole thing in natural language. In natural language. In natural language. Okay, so if F does not go to L as X goes to C, then there exists an epsilon such that for all delta, there exists an X not equal to C, and X minus C is less than delta, and I mean, I should be writing the words and, because is it or, is it, what are these things floating in midair? It's ands. X is not equal to C, and X minus C is less than delta, and Fx minus L is at least epsilon. Set delta equal to 1 over n plus 1, setting delta equal to 1 over n gives a sequence. This is what you'll see people write. How does it give a sequence? It's this choose and then setting the delta is equal to 1 over n gives a sequence xn going to C, never equaling to C, for which f of xn minus L is at least epsilon, contradicting the hypothesis, contradicting the assumption. That's the natural language proof. And that's how much it's hiding. Okay? Does that make sense? Now, there's one more thing we have to do. The fact that it contradicts the assumption.
Yeah.
Yes. In natural language, this would be enough because it would clear that it contradicts the assumption, but we have to prove it. So we need one more, there's one more step.
So you get from delta equals to 1 over n to x and converges to C.
Yeah, so for any delta, I get an x. So I said delta equal to 1 over n. That gives me, for every value of n, that gives me an x. Those x's are all less than 1 over n. 1 over n goes to 0, so the xn's go to C. They're never actually equal to C. But their f values stay away from L. That's a contradiction. Done. Next. Not so fast. Daniel.
Wait. This is contradicting the assumption that f of xn goes L, right?
No, it contradicts the assumption that for any sequence xn, the assumption is for any sequence of xn's, which are not equal to C but converge to C, f of xn goes to L. And now we found a sequence, we've constructed a sequence that satisfies the assumption that it's never equal to C and goes to C, but whose f values stay away from L by a fixed amount.
I'm still confused on which assumption to file.
The assumption is if you have a sequence of values going to C, then the sequence of f values goes to L. And then what we're trying to prove is that continuously f goes to L.
Right.
So if this fails, but the assumption holds, we're supposed to find a contradiction.
Right. So it contradicts that the sequence fxn goes to L.
Exactly.
Oh, okay. That's what I said, then you said it was wrong. I got it.
Oh, then I misheard you.
Okay. Yeah.
Contradicting the assumption. Yeah. Okay. Now so that's the natural language proof. That's nice, but how do we really do it? How do we get that contradiction? So we've constructed this sequence, which I've called U for some reason. Maybe I should have called these U's and made this X's, whatever. Too late. How do we finish it? Where are we going to find our contradiction? Well, we can prove things like have UNE, which says for all n, UN is not equal to C. And that we'll get from xn. Let's not bother with the proof. Jeffrey?
First proof that like U goes to C.
Right. And then we have that U what is this called? UC, I guess. UC is that for all n, UN minus C is less than, well, delta, but delta is 1 over n plus 1. So that means that it goes to C, but we haven't proved that. And then we have, what is this? FUL, which says that F of UN minus L is at least epsilon that we'll get from the FXL. And how do we finish it? There's one more step, Daniel.
You might specialize our, I don't know what it's called, the FX goes to.
Yes, I guess, didn't give this a name. What should we call this? HA for the main assumption or something. Yeah, we're going to specialize HA to UN. U is the sequence. So continuing from here, we specialize HA. U is the sequence. Y is the sequence never equal to N, never equal to C. That's UNE. And then Y is the sequence. Okay, so so now we're saying if the sequence converges to C, then this holds. So yeah, we could prove the convergence. So we would need to prove the convergence. Have U. There's a slightly better way to do this, but let's do it the sort of U lim says seq lim U C. And why is that true? Given this epsilon, which we should call something else, eta or something, how do we get within eta? Joe. Archprop, Archimedean property.
Wait. I think
Okay. So this says for all eta positive, there exists an n so that once U is past n, you're within eta. And we take n, how large do you have to take n? You take it as large as whatever comes out of archprop, 1 over epsilon. So that's U lim. Okay, so then maybe we'll have U lim first, and then we specialize this to U lim. And now the claim is that seq lim FUN goes to L. Specialize that to epsilon. That's where we're going to get our contradiction. Specialize whatever's left over here. I guess this is now HA. HA is still the same thing to epsilon and the fact that epsilon is positive. And that will tell us that there exists an n so that for all n greater than n, FUN minus L is less than epsilon. And then we'll just take little n equal to capital N. Take little n equal to capital N, and then we'll get our contradiction. Okay, does that make sense? Everybody following along? Let's do it. Okay, let's do this in, I think it's easier to see. Is this really as small as I can make it? I guess so. Okay, let's do this in, what's it called? Editor mode. So that we can see everything. I think it's just easier to see it in editor mode. Okay, so we're going to start with the proof by contradiction. By contra, H. All right, so our goal is false, and H is it's not true that fun lim at. I think if I push neg directly, it's not going to do anything because, H was what I called the original hypothesis that I now called HA, HB, so that we don't lose the original hypothesis. The original hypothesis is for any sequence, as long as that sequence is never equal to C and X goes to C, the sequence Fxn goes to L. That's our assumption. Our goal was to prove that F goes to L at C, and now we're going to negate things, and now our goal is to prove false. I think push neg at HB will not work. Yeah, it doesn't do anything because it doesn't remember what the definition is, so we have to change. So change, it's not true that for all epsilon positive, there exists a delta positive, so that for all x not equal to c, x minus c less than delta implies fx minus L is less than epsilon at HB. Did it work? Yes. Good. Okay, and now let's push neg at HB. All right, there exists an epsilon, it's positive, so that yada yada, let's choose it. So I'm up to this step, choose epsilon, epsilon positive, choose epsilon, epsilon positive, and then H epsilon using HB. Okay, so we have our epsilon, we know that it's positive, and then we have this whole thing. This is a function. It takes a delta and it returns x. Should I give this function another name, like t or something? So I can say xn is the sequence, or you don't care? Keep it the same as what's written. Let's keep it the same as what's written. What's written is choose x. Choose x, xne, xc, and fxl using h epsilon. And check out what we have. Come on. And check out what we have. Exactly what we thought we would. It's a function that takes delta to a proof that delta is positive to a real number x inside that window. Anytime you have a delta and that delta is positive, you can take x with that delta and the proof that it's positive, that gives you a real number. The distance between that and c is less than delta. That number is also not equal to c, but those numbers all differ from L by at least epsilon. It's exactly what we wanted. Okay, let U be a map from N to R, which takes the natural number N and sends it to X 1 over, let's make it N plus 1, and then by bound. Did it work? Looks like it did. Okay, let's have UNE, which is for all N, UN is not equal to C. I'm just going to sorry this for now. Okay, UN is always not equal to C. Why is it not equal to C? Because it's xn, x not equal applied to yada yada. Have UC for all N. Now what? Now this is a little more delicate. UN minus C is strictly less than 1 over N plus 1. Let's just sorry that. Okay. That comes from the X, together with the fact that delta was chosen to be 1 over N plus 1. And let's have, what do we call this? F, the F acting on U is near L, which says that for all N, F of UN minus L is at least epsilon. So I guess the better way to do it is like this. And let me sorry that. Okay, you guys believe all of these things? They come straight from the facts on X that we already proved. Now we're going to prove U lim. So have U lim, which is seek lim U C. Again, let me sorry that. Do you buy that the U's go to C? You give me a delta. I use ArchProf to find that delta so that happens. And what's the last step? Now we're in business. Now we're going to start specializing H. Specialize H. The first thing H wants is a sequence. What sequence will we feed into H? U. Why is U never equal to C? UNE. Why does U converge to C? U lim. And what that gives us is that the FUNs had better go to L. But the definition of going to L is for all epsilon there exists yada yada. Which epsilon do we feed into? Epsilon. We specialize this to epsilon. Why is epsilon positive? Because of epsilon pos. This says there exists an N with these properties. So I'm going to choose that N. Choose NHN using this. And now I have an N so that for any N after that point, this happens. So I'll specialize HN to what value of little n? Capital N. And why is it greater than itself? Uh-oh. That's going to contradict something else. What's it going to contradict? FUL specialize FUL to what value of n? Capital N. Now I've got this lower bound and that lower bound, and I think, what is it called? Contradiction or something? Contradiction. Really?
That's a good story.
Linarith, FUL against HN. And we're done. With warnings, because I have a bunch of sorries. Let me not fill in the sorries in the interest of time. Okay, you guys can fill in the sorries yourself. Cool? These are very subtle arguments. And the natural language versions of those arguments sweep all kinds of things under the rug. This is exactly why I wanted to do this form. Next, any questions? Brandon.
I just want to understand, so like the sorry statements are pretty much like contradicting an assumption in natural language. That's what basically the sorry statements are, or I think the first three sorry statements.
The first three sorry statements, let's do one of the sorries. Let's clean up one of the sorries. Okay. How do you get this? Which of the sorries is the, well, we should really do the hardest one. Let's do the hardest one. Let's do u lim. Okay. Why is u lim true? So let's work on u lim. We're trying to show now that u goes to c. So let me intro. I don't want to call it epsilon or delta, Daniel. Tab. Yeah, all I'm doing is tab. Uh-oh. I hope I didn't ruin everything by trying to make this slightly bigger and more readable. What I need is another thing so I can drag this down so I can see more of what's written here. But okay. So I'm going to introduce what? I'm going to introduce not epsilon, not delta, eta. Eta, H eta. Okay, so that tells me that I have a positive eta, and I want to show that there exists an n so that un minus c differs, un differs from c by eta. So choose NHN using archprop and the fact that eta is positive, I think is all I want. Maybe eta plus, yeah, eta is enough because 1 over n plus 1. Or no, it's not enough. I need to go a little bit bigger. Anyway, let me not waste our time proving this. This you guys can fill in the details. Right? You take it large enough, you're going to contradict, or you'll prove this by using UC together with the fact. Oh no, I am good because 1 over n plus 1 is at most 1 over n, which is at most 1 over capital N, which is at most eta. And then it's annoying, arithmetic to get it there. But I think you can fill in the details. Cool? Questions? Brandon, did I answer your question?
Well, yeah, I was just gonna ask, like the sorry statements, like in natural language, like that's just more explicit, like saying contradicting assumption. That's what most of the sorry statements are actually like further explaining.
Further explaining, exactly. They're further explaining things that in natural language you just say, well, obviously that's true.
Okay.
I just defined it that way. Why is UN of C different by 1 over n plus 1? I chose it that way from the choice of delta.
Right. Okay.
You don't bother saying these things again, but of course, if you actually want to use them, you have to spell them out explicitly. Okay, good. Next, let's go. So sequential limits. So things that look continuous can be measured by things that are discrete in both directions, if and only if. I'll give you as homework, I guess it won't be due this time. I'll give you as homework sequential, or maybe I already did. Maybe I already did. Sequential limit for continuity, which is slightly nicer. It's a little bit easier. You have one less thing to worry about. You don't need to worry about whether it isn't or isn't equal to C. All right, next. Let's compute a derivative. Hey guys, we're ready to compute a derivative. We have a new definition, fun deriv at. So before I show you what fun deriv at means, what do you think fun deriv at should be? So definition, fun deriv at. What should you be given? A function. What else should we be given? The derivative. What do you think the derivative is? I don't know. What do you want to call it? F prime, sure. F prime is a real number. It's not a function. It's a real number because it's the derivative at a point. At x equals c. In fact, maybe it's better to say, maybe because you think of f prime as a function. Let's just continue calling this L. Okay. What is this? It's a prop. It's either true or false, whether the derivative of f at c is equal to L or not. Well, Yeah, can we do it using,
Like,
yes,
like all.
let's use fun lim at. We already have the technology. The function that sends h to what? That function should go to what limit? L as h goes to 0. That's what the derivative is. Okay, and let's see if I thank you. Thanks. So let's see, where's our fun deriv? Well, it's right here. There it is. So fun deriv at is defined to be fun limit at the function that sends h to f of c plus h minus c, f of c divided by h. That should have limit L as c goes to 0. Cool. Let's compute our first derivative. X squared minus 1. What's the derivative? 2x. What is it at x equals 2? 4. So our job is to prove, so theorem. This is a good quiz. Theorem. Fun deriv, or is it too hard? I don't think it's too hard. Is it too hard? I think you guys can do it. Fun deriv at the function that sends x to x squared minus 1, I claim has derivative 4 at x equals 2. By. See if you can come up with a formal proof. Take 5 minutes. Talk to each other.
One more than like.
Start with an informal sketch and then see if you can turn it into a formal proof. Talk to one another. Raise your hand if you need a hint of proof. I want to see pictures. What do you think is to draw a picture? See a lot of text.
So that's it 4 too.
This?
Yeah.
So the function is this, the derivative is 4, and the c value is 2. So when x is equal to 2, the derivative of this is 2x, and 2x is supposed to be 4. I mean, the first step, you could try to do this. Let's do the first step together. I'll just intro epsilon h epsilon, and then you'll see what the goal looks like, which should be no surprise to any of you. What delta do we need to put there, given this epsilon? Talk to each other. Look at your neighbor's page. This is the time to do it. Who's got the value of delta? Still working? Start by simplifying this algebra. What is this algebra going to come out to? Question 2 on C. You got it. That's stupid.
That's. Yeah, it has to be. So far.
What'd you use?
I think it is.
Is the algebra tripping you up? Should we change this to make it a little nicer? Let's change this to make it a little nicer. What do you think the value is? Why can't I copy? Come on. I just want to copy this. Let's do a change just to make life a little bit nicer for us. So, this is the function that sends x to x squared minus 1 evaluated at 2 plus h, which is the same thing as saying just 2 plus h. And then I can get rid of that. And then this is the function that sends x to x squared minus 1 evaluated at 2. So this is just 2 squared minus 1. And then the function that sends h to this whole thing at x. Well, if I change the whole thing to call it h, and then I can just delete the fact that it's a function. I think that'll look slightly nicer. Oh no, I missed a parenthesis. 1, 2, 3, 2, 1, 2, 3, 2 over h. I thought I got it. -1? I have too many parentheses? 1, 2, 3, 2, 1, 2.
1. You have to remove.
Thank you. Ah. Still no good. Let's go to editor mode. Maybe I'll see it there. Reload. Okay. 1, 2, 3. 2.
I think the front. Then the arrows got changed.
All right. I tried to help you. Sorry. Okay. What delta do you want to use? Let's do it together. Okay. Let's do a calculation. Scratch work by scratch work. Scratch work, a picture. Scratch. So what's the picture? Our function is x squared minus 1. Just draw it. It's going to have roots at -1 and 1. It's a parabola, yada, yada. At x equals 2, so this is x equals 2, its value is 3. Its value is 3, but its slope is 4. Okay, that's what we're trying to do. The way we're going to measure the slope is by taking f of 2 plus h minus f of 2 dividing by h. What the heck is this then? Okay, well, the function is x squared minus 1. So this is 2 plus h squared minus 1 minus 2 squared minus 1 all over h. Okay, keep it going. This is 4 plus 2h, 4 plus 4h plus 1 plus h squared minus 1 minus, well, 4 minus 1 all over h. The way calculus works is anything without an h has to get canceled off. So that you have an h on top and an h on bottom. And this whole thing turns into h plus 4. That whole thing, I claim, goes to L, which means the difference between it and L goes to 0. So if I subtract, so H plus 4 minus L is 4, is just H itself. So what if I want this whole thing to be less than epsilon, how small do I have to make sure H is? What's delta? Epsilon. Okay, so I'm just going to use epsilon, comma, H epsilon. Okay, for all x. So give me that. I don't want to call it x. I'll call it H. Give me the fact that H is not 0. Give me the fact that H is less than something. And then this is what I need to show. So far, so good? Okay, this is god awful. Let's just change it a little bit. Let's see if I can get the change to work this time. So let's do it one step at a time. Let's change it to just 2 plus h, the function that sends h to 2 plus h. That works, okay? And then I'll change this to this thing. I'm not done. There we go. Okay, that worked. And now the function that sends h to that, if I just remove the function that sends and the h, that also worked. Okay, good. I don't know why it didn't work last time. Very good. So now we have 2 plus h squared minus 1 minus 2 squared minus 1 all over h, all minus 4 needs to be less than epsilon. All right, let's do a little bit of arithmetic. So rewrite, show that this whole thing is equal to, what did we say it was? H plus 4? No, h times h plus 4. So h squared plus 4h. I only did the numerator. By ring. By ring. Beautiful. Okay, so this is that. Now let's divide by h. Come on, out of the way. Out of the way. Rewrite. Show. This thing is equal to h plus 4 by field sim. Why is field sim going to work? Because h is not 0. It already knows that h is not 0. It's not going to finish the job because we have to. Oh, it will finish the job? Okay, it finished the job. Great. Field sim smarter than I thought. Okay, h plus 4 minus 4. I'm going to change that to. That's the good guess. And I'm going to be a little bit slicker than that. H minus 0. We're going to change h plus 4 minus 4 to h minus 0. So I have one less thing to do. Rewrite, show h plus 4 minus 4 is equal to h minus 0 by ring. Aha. Apply h less than. That, ladies and gentlemen, is our first derivative. Official, proper derivative. Not so bad. What do you think? Question, Daniel.
On an exam,
Yes.
if we were to just rewrite, show big thing in the absolute value equal to h by algebra, is that formal enough for you?
Yes.
Okay, right.
Something.
Or do we have to use like delta anywhere?
The delta, the very first thing, we got our epsilon. And then what value of delta? What value of delta do we need to guarantee that as long as h is within delta of 0, then this whole thing will be less than epsilon? Our big calculation said that this whole fraction, minus 4, is going to come out to h. How are we going to make h less than epsilon by making h less than delta? By setting delta equal to epsilon.
Let's say we got 2h,
Yep.
then would we say like epsilon of 2?
Yep. Let's do the next problem. You guys are good. You're anticipating everything, Damien. Scroll down. Yes, I'm sorry. Towards the end. Then I rewrote the algebra. And then we rewrote a little bit more of the algebra. And now we have h minus 4. And then we're done. Duhas, question?
No.
Next. Yes.
But what's the relation?
What's the relation between H and delta? So when we do this calculation, we want to be able to prove, that this f of 2 plus h minus f of 2 over h minus what we think the derivative is less than epsilon whenever h is less than delta. And so what delta do we need to enforce this as a function of epsilon? And when we computed what this came out to, it came out to h. So if we can make h less than delta, how do we make this less than epsilon? We just set delta equal to epsilon.
That's like, you can also just think about that, that's where like the h minus 0 comes from.
Yes.
That's like the whole limit thing.
Exactly.
And instead of epsilon, we're just using delta because we're already using.
Let's do the next example because we're gonna get something, right? You got to start with something simpler and then build it up. Here we go. The derivative function. So we know how to differentiate at a point, but of course the power of calculus is not to do it at one point at a time, but to do it at all points. So we have a new definition, fun deriv. Okay, so definition. Fun deriv. You have to give me two functions, a function f, that's the function, a function g, which I claim is the derivative function. And then I'll tell you yes or no, is one the derivative of the other, prop. For all x, fun deriv at which function? F at where?
So,
At x. What's the derivative? G of x. Excellent. You see that? Okay, so that's the new definition. For all x fun deriv at, f has derivative g of x at x. Let's do let's differentiate x squared minus 1 everywhere. Okay, so theorem. Maybe this is another good one that you could try on your own, but let's do it in the interest of time together. So I have functions f and g. I have f is equal to f of x is equal to x squared minus 1. I have g of x is equal to 2x. And my claim, my goal, is fun deriv fg. The derivative of x squared minus 1 is 2x. Step 1. Intro x. Yeah. So intro, maybe we should call it C. So we have this this thing, and we have this other function, which is 2x. And at any point C, can I prove that the slope of this is this value? So intro C. Great. Now I have to show fun deriv at f g of c c. What do we do? Intro epsilon. Okay. So intro C, intro epsilon, epsilon positive, I guess, or I called it H epsilon, fine. All right, so we have to provide a delta. So this is just a slightly more involved calculation. So sketch work. We need f of c plus h minus f of c over h minus g of c. That whole thing needs to be less than epsilon. What should we do with h to ensure that this happens? Okay, so this is what we need. We need this. Let's do some algebra. F of, let's see. It's a little more subtle than that. Let's see. So we have, this is going to be, remember the function is x squared minus 1. So this is c squared plus 2ch plus h squared minus 1. That's f. Minus c squared minus 1. That's f of c. All over h. Minus g of c. G of c is 2c. Okay? That's what this whole thing on the inside is equal to. All right, C's got to go, -1's got to go, so that all that's left has an H in it. Let's kill that H, let's kill that, and what do I get? We just get H. Okay, so you're right. Everybody see that? It's an H plus 2C minus 2C. So again, for the same exact reason, we can use delta equals epsilon. I think the next one is one that, oh, is it a homework? Let's see. I don't remember what I gave you. Use delta and use rather epsilon and H epsilon. Okay, intro X, intro H, H not equal to 0. What did I call this? H less than. Okay, so we have H is now a real number. It's not equal to 0. It's less than that. What's this function? Can we change? This is an easy change. Change. That's the nice thing about not using explicit functions, but doing it just in terms of abstract functions. Okay, great. Now let's rewrite f of hf. I want to know what f is, and I also want to know what g is. I think I have to rewrite hf twice. Once for this one, once for that one, and then g. Great. It automatically figures out. It sees the first instance of f, rewrites it. It sees the second instance of f, rewrites it. It sees g, rewrites that. Okay, now let's do a little bit of algebra. So rewrite, show that this thing is equal to the same thing by ring, except it's not the same thing. I want this to come out to what? H squared plus 2ch. Yeah, exactly. H squared plus 2 times C times H. Hopefully the parentheses were okay. Uh-oh, the parentheses were not. I did that too fast. Let's go back to typewriter mode. I mean, editor mode. Okay, very good. All right, we got that. And now let's get this quotient to be better. Rewrite. Show this is equal to by this looks good. Let's kill the H and that H and that division. And that's by field simp. And nothing else. Beautiful. And now this thing's equal to that thing. Okay, so that's easy. I'll rewrite show this is equal to H minus 0 by ring. Come on. And exact apply HLT. Okay, let's do the next one. So this makes sense? So now we have derivative at a point. Now we have derivatives, functions as derivatives. Next. Okay, continuity everywhere. Let's talk about continuity everywhere. Where are all my other, I think I have a lot more things for you, but maybe I didn't load them here yet. New theorem, or new definition. So we can differentiate anywhere. Let's talk about continuity anywhere. Fun, continuous. So you give me the function f. What does it mean for the function to be continuous everywhere? For all x, the function is continuous at f x. Okay? And the theorem is this function. The function f of x is equal to what? X squared minus 1. Why not? Let's stick with our old friend. Is continuous. Okay? Bye. Now we're going to see, I knew I had one coming. Now we're going to see something where you have to do something less trivial. Okay. What is function continuous? Intro, very good. Intro x. Yep. Intro x. Intro x. Let's do it. Come on. Okay. And then intro epsilon h epsilon, which of course you could do in one line. Okay. There exists a delta. So now we have to do a little bit of work. Why is it continuous? So if I have some new variable. Let's call this, I don't like to call it y. I think of y as the vertical. Let's see. Maybe if this is, so here's our parabola again. Here's some point x. Maybe this is u. You like u? Sure. Sure. Anyway, this thing is supposed to be h. If h, no, that's not right. That's x. That's x. Okay. So this will be c, this will be c, and this will be x. Great. Okay. So we want to prove that x squared minus 1, so sketch work, x squared minus 1 minus the x squared minus 1 evaluated at c, also known as c squared minus 1, that needs to be less than epsilon. How do we get that to be within epsilon? By making x and c close enough. So this is what we want. We want this, assuming x minus c is less than delta. So what value of delta do we need to take? Okay, the ones cancel, and I have x squared minus c squared, which we know is x minus c times x plus c. X minus c we can make delta. How about x plus c? Very good. We can write x plus c as x minus c plus 2c. And we could make this, we could make our lives very complicated by saying this is at most delta plus 2c. Or we could say, let's make sure that delta is less than 1 if epsilon happens to be large. So also assume delta is less than 1. Then this will be at most 2c plus 1. So we can make this whole thing less than delta times 2c plus 1. And we need to make it less than epsilon. So need, just to spell it out, delta times 2c plus 1 less than epsilon. So choose delta equal to epsilon over 2c plus 1. Does everybody see how we got that? So this is an example where it's not just delta equals epsilon. And in fact, it depends on the value of c. Delta needs to be, as c goes out to 1,000,000, delta needs to be much smaller than epsilon. Okay, the next topic is uniformity. We're not going to get to it today. All right, so use epsilon. Well, let's do a let delta equal the minimum of 1 and epsilon over 2 times the absolute value of c plus 1. Have delta positive, or h delta or something, is that delta is positive. Let me not waste time proving that. So what do I want to use? Yeah, before I use it, let me record one more thing. Delta 1 is that delta is less than or equal to 1. Maybe bound will do this for us. Thank you. And let's have delta 2 is that delta is less than or equal to this whole thing. Let's just record those because we know we sometimes need such things. Okay, now let's use delta and h delta. Okay, give me an x, intro x. Give me the fact that x is within delta of c, hx. And now I need to prove this thing. Let's make this look a little nicer. Change. This does work nicer when it's functions instead of explicitly making the function. That's going to be a c. Okay, change works. Beautiful. Then let's grab this algebra and do some, come on. Grab this and do a little bit of algebra on it. Rewrite, show this thing is equal to x plus c times x minus c by ring. Yes, yes, good. Okay, let's grab the absolute values and break those up. Rewrite, show absolute value of this thing is equal to the absolute value of this guy, oops, times the absolute value of that guy by apply abs mul, I believe. Okay. Now, well, let's start by saying this is at most delta. What's that? I want to say that x plus c times x minus c is at most. Okay, let's work on x plus c. So our claim is that x plus c needs to be at most 2c plus 1. So I'm just going to state that right now. I can't call it f. Oh, I can call it f. I started calling it, I started running into problems when I call facts f if I don't number the f, because we have functions called f. And it kills the function. Okay, so have f1 is that we're going to have to prove that x plus c is less than or equal to, what is it? 2 times absolute value of c plus 1. And let me sorry that out for a second. We'll come back to it. So this is at most that. Delta is at most that. So should I teach you calc blocks? So this is less than or equal to calculation blocks times x minus c. I wasn't going to cover this because the game doesn't do this very well. This is by, why is that? By bound. Maybe bound will do it. Very good. Yeah, it's complaining that calc isn't available in the game, but it's letting me do it, isn't it? Let's call this f2. So I'll show you. It lets you do this.
Oh. What is it? Oh. Wait, what? What am I?
Oh, come on. Bound can totally do that. It knows that x minus c is less than delta.
Wait, what is going on?
So this is why I'm not teaching it to you. It's a way to chain a whole bunch of inequalities. It's the right way to change inequalities, but the game doesn't support it. I'm just going to sorry this. And then what's the point that x plus this is less than delta, but delta is equal to, delta is less than epsilon over this thing. So I'm just going to copy all of this and it's, how does it do the weird blocky thing?
Like how do you put it?
Press tab.
I'm just hitting tab. Yeah, I'm just hitting space enough times. And then this delta is less than epsilon over 2 times c plus 1. And that's by bound. Oh, come on, bound. Get better, bound. Okay, so that's our F2 so far, is change all of these things together, and that's equal to, and that is equal to epsilon. Will bound do that one? No, still no. Screw you, bound. What do you know? I bet grind will do it. Okay, so F2, I think, when F2 is done compiling, is exactly what we want. So then apply F2. All right, it's with some cheating. With some cheating and a calc block to speed things up, instead of writing all these things out individually. What I've taught you to do is approximate calc by writing each of these one by one, and then linearith to chain them all together, but calc does it in one fell swoop. Okay, I think that's going to be, I don't need to fill in these sorries. You guys are okay with filling in the sorries, and you're also okay with, maybe when we have the blocky version, it'll support calc. And we'll be able to just do a calculation like this. Can you guys see this calculation? Should I pull this over so you can at least be able to see it all in one fell swoop? Very good. That's all the time we have.